There is a story we tell ourselves. It appears in our films, in our novels, in the speeches of visionaries who stand before crowds and promise that one day the human species will scatter itself across the galaxy, seeding distant worlds with our biology, our culture, our restless ambition. We picture enormous starships threading the void between solar systems. We imagine colonies on the moons of Jupiter, domed cities on the red plains of Mars, generation ships drifting through the dark between the stars for centuries. It is a beautiful story, and the physics of this universe at almost every level conspires against it. I want to be careful here. This is not pessimism for its own sake. It is not a call to abandon curiosity or to stop looking up at the sky. What I am about to lay out is simply what the equations tell us, what the constants of nature have locked into the structure of reality itself. When you follow the physics honestly, without blinking, you arrive at a picture of the cosmos that is simultaneously more awe-inspiring and more humbling than any science fiction narrative has ever captured. And at the center of that picture is a universe that does not appear to have been engineered for the convenience of biological creatures with ambitions to roam. Let us start with the most fundamental obstacle, the one that exists not because of any engineering challenge, not because of any lack of funding or political will, but because of the deep mathematical structure of space-time itself. Einstein showed us something in 1905 that has never been overturned by a single experiment in more than a century of testing. Nothing that carries mass or information can travel at or beyond the speed of light. This is not a technological limitation. It is a geometric fact about the universe we live in. As an object with mass approaches the speed of light, the energy required to push it faster climbs without bound. You would need infinite energy to reach the cosmic speed limit, which means reaching it is not a matter of building a better engine. It is a matter of the universe simply not permitting it. Now, the speed of light is fast by any human measure. 300,000 kilometers per second. A beam of light crosses the continental United States in about 17 milliseconds. It circles the entire Earth in roughly 1/8 of a second. These are numbers that feel like freedom, like the universe must be easily navigable. But the universe is not the Earth, and it is not even the solar system. The nearest star to our own sun, Proxima Centauri, sits roughly 4 light years away. That means light itself, traveling at the absolute cosmic speed limit that no material object can ever match, takes 4 years to make that journey. A spacecraft traveling at 10% of the speed of light, which would require an engine technology so far beyond anything we have ever built that it strains the imagination to even describe, would take 40 years to reach our nearest stellar neighbor. 40 years. One human lifetime aimed at a single destination, and we would arrive to find a red dwarf star whose closest planet appears to be a tidally locked rock baked by radiation. The Milky Way galaxy spans roughly 100,000 light years. There are places in our own galaxy from which a light signal sent today at the cosmic speed limit would not reach the other side until roughly 100,000 years from now. The human species in its anatomically modern form has existed for perhaps 300,000 years. We have had writing for about 5,000 years. Civilization in any recognizable sense is a few thousand years old. The idea that we would sustain a coordinated interstellar project across timescales of tens of thousands of years is not merely logistically difficult. It runs against everything we know about how complex systems, institutions, and species themselves change over geological and cosmological time. But let us go even further, because the challenge is not just about distance or time. It is about energy at a scale that reveals something fundamental about our place in the hierarchy of the cosmos. The Tsiolkovsky rocket equation is a piece of mathematics that any first-year physics student encounters, and it is quietly devastating. It tells us that to accelerate a rocket to a given speed, the mass of fuel you must carry grows exponentially with the desired final velocity. To send a crewed spacecraft to even a fraction of the speed of light, the fuel requirements become not merely impractical, but cosmically absurd. At 1% of the speed of light, the fuel-to-payload ratio for a chemically propelled vehicle approaches numbers that exceed the mass of entire planets. Even with the most optimistic projections about exotic propulsion systems, whether we imagine ion drives, nuclear pulse propulsion, or laser sails, the energy budgets required to move significant mass at interstellar speeds exceed what the entire human civilization currently produces in centuries of total energy consumption. There is a concept in physics called the Kardashev scale, which attempts to classify civilizations by their energy consumption. A Type 1 civilization, which we have not yet achieved, harnesses all the energy available on its home planet. A Type 2 civilization harnesses the total output of its star. A Type 3 civilization draws on the energy of an entire galaxy. Interstellar travel on any significant scale does not become plausible, even in theoretical terms, until you are approaching Type 2 energy consumption. We are currently, by most estimates, somewhere between 0.7 and 0.8 on this scale, still struggling to move completely away from burning ancient carbon deposits trapped in the crust of our own world. The gap between where we are and where the physics demands we be is not a gap of decades. It may be a gap of millennia if it can be crossed at all. And then there is the biological problem, which sits quietly beneath all the engineering discussions and rarely gets the serious attention it deserves. The human body evolved over millions of years inside a narrow, almost absurdly specific set of physical conditions. It evolved for a particular gravitational field strength, a particular radiation environment, a particular atmospheric composition, a particular magnetic field provided by the Earth's molten iron core. Spend extended time in microgravity and your bones lose density, your muscles atrophy, your vision degrades as intracranial pressure builds. Your cardiovascular system restructures itself in ways that may not be reversible. Your immune system behaves unpredictably. The radiation environment beyond low Earth orbit, where the Earth's magnetic field no longer provides its shielding, delivers doses to astronauts on long-duration missions that measurably increase cancer risk. On a journey to Mars lasting 6 to 9 months, a crew would absorb radiation doses that current estimates suggest represent a significant lifetime cancer risk increase, and that is for a journey within our own solar system. Now extend this to interstellar travel. Even setting aside the question of how to propel a ship across light years, any crew making such a journey would need to survive in an enclosed artificial environment for decades or centuries. The psychological literature on isolation and confinement drawn from submarine crews, Antarctic research stations, and space station inhabitants paints a picture of cognitive and emotional deterioration that becomes severe on timescales of months. Scaling this to decades or generations is not a solved problem. It may be a problem without a biological solution, because the human brain, shaped by evolution in small social groups embedded in rich natural environments, does not appear to be engineered for multi-generational existence in a metal cylinder drifting through the dark. Some people propose sending not humans, but their genetic information, or frozen embryos, or digital copies of human minds. These are fascinating ideas, but they represent a quiet acknowledgement that humans themselves cannot make the journey. And a digital copy of a human mind, if such a thing were even possible, would not be the humans who sent it. It would be something else entirely, something that raises profound questions about continuity and identity that physics alone cannot answer. Let us talk about the destination problem, because even if we could solve the propulsion and the biology and the psychology, what would we find? The search for planets in habitable zones around other stars has accelerated enormously in the past 2 decades. We have found thousands of exoplanets, and the statistics suggest that rocky worlds in the habitable zones of stars are common throughout the galaxy. This seems encouraging until you probe the details. A planet in the habitable zone of its star is not a planet with liquid water on its surface. It is a planet at the right distance to potentially have liquid water under the right atmospheric conditions, with the right geological activity to maintain those conditions over billions of years, without being tidally locked to its star, without being regularly sterilized by stellar flares, without having a Jupiter analog in the outer solar system to deflect the kind of constant comet bombardment that would otherwise make complex life impossible. The number of conditions that had to be simultaneously satisfied for Earth to become what it is represents a filter of extraordinary specificity. Whether that filter is common or rare, we genuinely do not yet know. The Fermi paradox sits at the heart of this question, like an unanswered letter. If the galaxy is ancient, if stars have been burning for billions of years before our sun ignited, if planets like Earth are common, then a civilization that achieved even modest interstellar capability a few 100 million years before us would have had time to spread through the entire galaxy, even at small fractions of the speed of light. The galaxy is 12 billion years old. We see no signs of anyone, not a signal, not a structure, not an artifact. The silence is not merely surprising. It is, if you take it seriously, one of the most important empirical facts about the universe that we have. It suggests something about the difficulty of the path from a curious biological species to a genuinely spacefaring one. It suggests that if there are others out there who have faced the same physics we face, the physics has been winning. Now, none of this means humans will never leave Earth in any meaningful sense. We will almost certainly establish some presence on the moon again. A crewed mission to Mars within this century is plausible, though the obstacles are formidable. A small permanent outpost somewhere in the solar system is within the realm of what our civilization might achieve over the coming centuries. These would be extraordinary accomplishments. The solar system itself is vast and rich with places that reward exploration, from the methane seas of Titan to the subsurface oceans of Europa to the volcanic intensity of Io. There is a lifetime of discovery within the gravitational embrace of our own sun, achievable in principle with the physics we know and the engineering we can envision. But a space civilization, in the sense the word is usually meant, a species spread across the stars, weaving its presence through multiple solar systems, maintaining contact and coherence across interstellar distances, this is what the physics does not support. Not because we lack imagination, not because we lack drive, but because the universe has a speed limit, and the universe is vastly larger than that speed limit makes navigable on any timescale that maps onto the continuity of a civilization. There is something worth sitting with in this conclusion. The same physics that reveals this limitation also reveals an extraordinary thing. It reveals that the Earth is not one world among countless accessible others. It reveals that this particular configuration of rock and ocean and atmosphere and biology, shaped over 4.5 billion years into the only world we know contains life, is not a draft to be improved upon somewhere else. It is the thing itself. The finitude of our reach does not make the universe small. The universe is incomprehensibly large, and most of it will forever lie beyond any journey we could take. That is not a failure of ambition. That is a measurement result. It is the universe describing its own geometry to us, and the geometry says that what we have here on this particular rocky world orbiting this particular middle-aged star in an unremarkable spiral arm of a galaxy containing hundreds of billions of other stars is not a starting point. It is the point. The full weight of that is difficult to hold in mind, but physics is not in the business of flattering our preferences. It is in the business of telling us how things actually are. And how things actually are, it turns out, is something stranger and more significant than any story we have told ourselves about our future among the stars.